A four-quadrant analog multiplier is implemented in this circuit using 4 op-amps and 4 BJT or bipolar transistors and then number of resistors. So we want to show that the V out is just simply in this circuit V1 times V2, so purely multiplication. And the nice thing about that is it's 4-quadrant. So basically, if you have V1, V2 on X and Y axis, positive and negative values for V1 and V2 without any problem is allowed, as long as, given that we have 5 volt here, as long as the absolute value of V1 and V2 is below a threshold, say 10 volt or lower than that. So that's the beauty of this circuit. Let's see how it works. Okay, so imagine that we have a BJT transistor, let's say T1, and transistor T2 here, and also T3 and T4 here. Okay, so as you can see in the transistor T1, we can see that if you chase the flow of the series of voltages from ground here, we have the base of transistor T1, and then we get to emitter. So there's from there, you can see that we have from 0 volt at base, we have plus minus VBE, and then we get to base of transistor T2, so that's B2. And then from there, you can see that we also have another plus minus VBE2 drop to this common node, which let's refer to as a common node. So, or let's say just to be easier to refer to that, let's say emitter, E. Okay, the same story applies to T3 and T4 as well. As you can see in these two cases, from the 0 volt at the base of T3, we are dropping 1 VBE, so VBE3. And then we get to the base of transistor T4. From there, we drop another VBE, which is VBE4, to get to that common node as well. So based on comparison provided here, I would say using Kirchhoff voltage law, or just basically the KVL, I can see that VBE1 plus VBE2 is equal to VBE3 plus VBE4. So this is very interesting, because this is allowing me to just now substitute for this base emitter voltage using Shockley equation of BJT transistor, which basically the Shockley equation, as is well known, is saying the voltage of base emitter of a BJT transistor that is operating is simply eta Vt. Eta is the ideality factor, a number between 1 and 2. And then we have natural logarithm, and then we have the collector current, or the current of the BJT, divided by the saturation current of transistor. And in this case, Vt is just Kt is the thermal voltage, and is K Boltzmann constant times temperature of junction in Kelvin divided by Q, which is the electron charge. As a reference, I have listed these constants here, Q and also K, Boltzmann constant here. T is in Kelvin for just junction temperature, and we are making the assumption that these 4 transistors shown here, these 4 BJTs, they are similar in terms of the junction property, so they are on the same substrate and they are copy-paste literally of each other. So with that, I'm going to substitute these guys using the Shockley. So using the Shockley equation, I'm going to just substitute, and then I am going to get eta Vt, so natural logarithm, and then the current of transistor 1 divided by the saturation current, so saturation current, plus again eta Vt, and the natural logarithm of the current of transistor 2 divided by saturation current. And remember, transistor T1 is here, T2 is here. So I am following those 2 transistors. On the other side, we have the same thing going on, eta Vt, and then we have ln of current of transistor 3 on top left, on top right, and then we have eta Vt, and finally the current of transistor 4 divided by saturation current. So let me shift this whole thing so that there is enough space to show you. Okay, so there you go. Okay, so what is going on here now? All right, so we can get rid of the eta Vt, so this one cancel out on all sides, And then what I get after this line, I have effectively ln, and then ln of 2ln summed up together on one side. I can just multiply the argument. So I1, I2, is squared equal to, again, on the other side, natural logarithm, I3 times I4, is squared. So since logarithm is a one-to-one function, therefore I can just say basically from this equation that the arguments are equal to each other. So is squared is equal to I3 I4 is squared. Since we are making the assumption transistors are exactly copy-paste each other, sharing the same junction properties, is the same for all of them, so we cancel out, and therefore we get to the famous equation for the current of these four transistors, the collector current. So I1, I2 should be equal to I3, I4. And that's making the life much easier because now I just need to substitute for these currents. So let's refer to this as equation 1. Okay, so I just need to find these currents. I1 is the current of collector of transistor 1, so basically that is this current, I1. And you can see that it's not easy, it's not hard to find that because if op-amp 1 is properly biased, so the positive negative supply voltages, let's say plus minus 10 connected, so that op-amp is operating in linear region, then the virtual short is valid, and if the virtual short for op-amp is valid, assuming op-amp is operating in linear region, it is saying that the voltage at the positive input terminal of the op-amp or non-inverting terminal should be equal to the voltage at inverting terminal or negative. So given this, you can see that the voltage at the positive is 0 connected to ground, therefore a virtual ground appears at negative terminal, making the voltage here 0 as well. So that is exactly 0 volt here. That makes my life easy because I can find easily this current, let's say current IA, and I can find easily this current IB, because IB is now, if I change the color, so IB is now, let's say IA for the time being. So IA is the voltage across this resistor R, which is 5 minus 0. So it is obviously 5 over R. So 5 over R amp. And you can see that the IB is the same thing in the same mechanism. Voltage across this 2R, which is V1 and 0. So it would be just V1 basically across 2R. So we have V1 divided by 2R. All right, so I am going to use this quick outcome, because what I can say is this I1 that is flowing through the transistor T1 in the collector is just the sum of IB and IA. That's it. So I am going to say, in this equation 1, let's substitute, but maybe I can put it this way. I1 is IA plus IB, as I showed, and IA is simply 5 volt divided by R, and you can see that, okay, so you can see that IB, as I said, is V1 over 2R. That's the I1, so I'm going to write I1. So let's refer to this as equation 2, okay? I can repeat this for, let's say, the other transistors. Let's say for T2, you can see that there is a current coming down here, and that current obviously is same argument as before. You can see that the op-amp 2, if it is properly biased to plus minus 10 volt supply, let's say, and it's then in linear region, virtual short is valid, and then positive terminal that's 0 volt connected to ground. As a result, the negative terminal also should see a virtual ground, so 0 volt, which means this point is 0 volt. And therefore, the voltage drop across this resistor, so across this resistor, is now known. Okay, so the voltage drop across this resistor is, if I can get rid, okay, so the voltage drop across this resistor is now known, plus minus R, and it is 5 minus 0. So what I can say is the current of the transistor T2 is the sum of this current and this current. So these two currents adds up and become the current of transistor T2. Okay, so let's write them. I would say the current of transistor T2 is equal to the top current is 5 divided by R, because that's the voltage across R. So 5 divided by R. And this current is now the one that is coming from V2 through the 2R. So it's just V2 over 2R. So it's V2 over 2R. Okay, great. Let's keep this as equation 3. Let's now write the same thing for transistor T3 and transistor T4 as well on the right side. So the collector of T3, the current, is of course nothing is coming from the input terminal of the ideal op-amp, because nothing can go through or come out because it has practically infinite impedance. So the only current that is coming in this case is just purely this current, which is, as you can see, if this op-amp 3 is also properly biased, so it has plus 10 volt, let's say, and minus 10 volt as an example. So its linear region of operation, virtual short, is going to be valid, and that means positive and negative input terminal should have the same voltage. You can see that positive terminal connected to ground, so it's at 0 volt nominal. So there you go, it at 0 volt nominal. Therefore, this should be 0 as well here. So virtual ground, this is 0. So that means the voltage drop across R is just 5 volt. So this current, therefore, is just I, which is I3, is just 5 volt divided by R. Okay, so let me just write that that one here as well. So I'm going to write I3 is, okay, maybe I just write it here. So I3 is 5 over R, and that's my equation number 4. Lastly, for I4, there is this current that is a little bit involved because it has a couple of components contributing to it. So we have one here, which is obviously for the same reasons discussed, because op-amp 4 is properly biased, plus minus 10 volt supply nominally, and therefore virtual short valid positive terminal is 0 volt, and therefore negative terminal is 0 volt as well. So here we have 0 volt. So therefore we can easily compute this current, which is VO, this current here. So let's say this current is simply VO minus 0. So this current is VO over 20R. Because you can see that across 20R we have simply just V out. And this current is obvious here for the same reason that here we have 0 volt. The voltage across this resistor here is just purely 5 volt. So this current is 5 over R. Okay, great. So the only thing remaining is what is coming this way or not, or going that way. Okay, so that is again not difficult because here is 0 volt, and you can see that across this 2R we have a V1. So basically this current as a result is just V1 divided by R, 2R. And then the same thing for this current. For the one that goes through the lower 2R, you can see that across that we have 0 and V2. So therefore, that current is V2 divided by 2R. So what I'm saying is, this current that is going toward the last collector we want to talk about is simply V1 plus V2 divided by 2R. The sum of the two currents that are adding together in this node, writing a KCL effectively. Okay, so what I'm going to write as the KCL, last KCL at collector 5, so I'm going to say Kirchhoff current law at, collector of transistor 4, collector of T4. So you can see that we have a bunch of currents coming and forming the current of collector 4. So this is I4. Some of the other components coming. So it's effectively is 5 over R plus V out over 20R plus finally V1 plus V2 divided by 2R. Okay, so let's highlight this as the last equation we need to solve the problem. So this is equation number 5. So what I'm going to do is now I am going to use all the equations at once. So I'm going to substitute for these 4 currents, I1, I2, I3, I4, in equation 1 using what I found. So by using 1 and substituting 2, 3, 4, 5, what I get is 5 over R plus V1 over 2R, that's I1, okay? Substituting for I2, which is from equation 3, as you can see here, I have 5 over R plus V2 divided by 2R, and that's the left-hand side. Right-hand side substituting for I3 here. So I'm going to get, using equation 4, I'm going to get 5 over R, and finally the last one is of course substituting for the more involved I4 using equation 5, which then becomes 5 over R plus V out over 20R plus V1 plus V2 divided by 2R. So the beauty of this whole thing is if you simplify this equation, you will see that a lot of things will cancel out. So you will end up actually seeing that, as an example, you will see that these components will cancel out. Let me highlight them, which one I'm talking about. So this one cancel out with this, and the only thing from both sides. Let me write it so that it's obvious what I'm saying. So because the outcome of this thing is just we get the final result that we are looking for. So what I'm going to get is on this side, and we can get rid of R in denominator because you can see R in denominator appears in both left and right sides. So what I'm going to say is 25 and then plus 5 times V1 plus V2 divided by 2 plus we get V1 divided by V1 times V2 divided by 4, and I got rid of R squared from all sides. So, and then the other side I'm getting 25 plus V out divided by 4 plus V1 plus V2 divided by 2, or 5 times V1, sorry, 5 times V1 plus V2 divided by 2. So you can see now in a more clear fashion that this 25 cancel out this 25, this 5 times V1 plus V2 cancel out this one, and then what remains is this guy is equal to that. And of course 4 will just disappear from denominator, and we get to the famous outcome that we were chasing. Basically V out is equal to just simply V1 times V2. And as I said, the beauty of this is we can have negative voltages as V1 and V2 at the input of the circuit. It's not just a single quadrant, it's 4-quadrant. So V1, V2 can be negative voltages as well, of course, assuming that, as I said, they are the absolute value of V1 and V2 is below a threshold, which in this case is a very practical, reasonable threshold like 10 or 9 volt. It might be safer to go, let's say, 5 volt. But bear in mind that the way we are done, I hope that this is helpful, but as a practical, intuitive point, please bear in mind that the circuit is working in this way, and in order to realize 4-quadrant and the possibility of V1, V2 being able to being negative voltages, is in a way that actually 5 divided by R is providing a current for, let's say, collector of transistor T1 and collector of transistor T2. In the case that we have negative V1 voltages that require then a source of current toward the V1 basically. So they're sinking current in that scenario. And that sinking current, while the 5/R is providing the needed current for collector, in that scenario it would provide also the needed current toward V1 when V1 is negative voltage, of course, assuming V1 is satisfying the requirement that it should not be more negative than a specific value, otherwise the circuit would not work. Okay, so I hope that this example is helpful in terms of showing that how an analog multiplier, a practical analog multiplier, is designed, and four-quadrant version, and how we can select the choice of resistors and parameters in the circuit so that the equation just becomes exactly like a perfect multiplier we are chasing, V1 times V2. Of course, if you want more gain, you can always adjust the value of this final resistor, or it can even be a potentiometer if you like to have some flexibility in the circuit. I hope that this example is helpful.